Hello students, this is lesson 9, cell notation and standard reference cells. I'm actually in a hotel right now, and so my audio quality is probably not great. I don't have my mic here, but anyway. Okay, so cell notation, we talked about this a little bit in a previous lesson, but cell notation looks like that. You have an electrode, line, electrolyte, double line, electrolyte, line, electrode. So you can see right there's my electrode, then I have my electrolyte, salt bridge, electrolyte, and then my line, which just represents a phase boundary, like that's aqueous and the electrode's solid. So anyway, okay, so I write my copper, sits in the copper 2 ion, I got my salt bridge or a porous cup, zinc, and then the zinc solid sits in the zinc 2 solution. Then I gotta know my net voltage, so I can quickly look at the chart, find my SOA, find my SRA. Of course, I've got to flip that reaction, and if I flip the reaction, I need to flip that to positive. Okay, I'm going fast because this is a review. Add those together, I get my net voltage. So, so that is cell notation. You list your electrodes, electrolytes with your lines, your salt bridge line, and then you put in what your net voltage is, and that's it. That's cell notation. Okay, so I'll skip through all that. Okay, next. Now we're going to determine an unknown half reaction voltage. So you can see right now they've given us this copper germanium cell. They've told us the net voltage. We don't have to go calculate it. There it is. But if we check our data book, germanium is not in our data book. So determine the reduction potential for Ge4 positive. What do I know right now? I know that this is positive volts, right? So I know that my OA is above my RA. I know that. I also know what my anode is. My anode is germanium. They already told me that, which means that must be my strongest reducing agent because loss of electrons oxidation occurs at the anode. So Ge has to be my strongest reducing agent. Okay. I also know that my strongest reducing agent or my strongest oxidizing agent gets reduced at the cathode. So Cu solid is the cathode, but it's not the SOA because it's usually that ion. The copper solid is on the reducing agent side of the chart. So there's my strongest oxidizing agent, which gets reduced. Gain of electrons reduction occurs on the surface of the cathode. So I also know that that has to be Cu2 positive. If I know those two things, then I can start writing my reactions. Copper 2 gains 2 electrons, turns into copper solid. I already know its voltage. It's positive 0.34 volts. I do know what this reaction is. I know it's an oxidation reaction. It's not on my chart, but I can look at this and guess it's going to look like that. Germanium is going to turn into Ge4. Now, what I don't know is its voltage. But here's what I do know. I do know my final voltage is 2.36 volts. Therefore, the missing voltage has to be 2.02 volts. Because 2.02 plus the 0.34 makes 2.36. Now, let's look at what the question was asking. Like, we might think we're done there. We just found the unknown voltage of 2.02 volts. Except the question was asking, what is the reduction potential for Ge4 positive? This is an oxidation reaction. And so I have to flip my reaction to make it a reduction equation. And therefore, I have to flip my voltage to negative 2.02. And that is the answer to this question. Okay, so that's how you find an unknown half reaction voltage. Okay, Now it says this one is determining half reaction voltages as if hydrogen were not the reference cell. Okay, so on our data book right now, the hydrogen cell has a voltage of 0.00 volts. That is an arbitrary designation. Okay, we've made that hydrogen the zero cell, but it doesn't have to be. Okay, if you notice in your data book, everything above the zero cell is positive, every voltage is positive, every voltage below that is negative. Okay, so if you look at the chromium reaction, it's at negative 0.91 volts. And if you look at the copper reaction, it's at positive 0.034 volts. Okay, so what principles do you need to know to do this question? First, the standard reference cell is the zero cell. Okay, the hydrogen cell is the reference cell. All other reactions on the chart sort of refer to it because it's at zero. Okay, this is an arbitrary designation. We can pick any one of those to be the zero cell. And all reactions above are positive, all reactions below are negative. And the difference between any two voltages on the chart is always the same. That's the other principle that's really important. So the difference between hydrogen and copper is 0.34 volts. It doesn't matter which cell we choose to be the, quote, reference cell. The difference between hydrogen and copper will always be 0.34 volts. Okay, the difference between those two will always be 0.91. So knowing those principles, that the hydrogen cell is the zero cell and that it's an arbitrary designation, and that the difference between any two is always the same, we should be able to readjust the chart for this question. So here's the question. Assume chromium is the reference cell, not hydrogen. What would be the reduction potential for copper 2? Okay, so here we go. Our chromium cell is now the reference cell. Because it's an arbitrary designation, we're just going to call that 0. All right, the difference between chromium and hydrogen is always 0.91 volts. Remember, everything above 0 is also positive. So hydrogen's new voltage would have to be 0.91 volts because the difference between those two has to be 0.91. And everything above 0 is positive. All right, now let's look at this one. The difference between those two is 0.34 volts. So if I just take 0.91 and add 0.34, I get my voltage of 1.25, which is the answer to the question. If the chromium cell is 0, the reduction potential for the copper 2 reaction is 1.25 volts. Okay, all right, that's it, ladies and gentlemen. There's some work to do in that lesson, so go ahead and do it. All right, we'll see you next time.